Welcome to Section 2, Introduction to Fraud Detection. This is Lecture 7, Sampling with a Class Imbalance. So in this first code block, I am importing pandas, and then I'm reading in the credit card CSV file that was presented in the previous lecture, and then I'm simply printing out the head to see the first 5 rows of the data frame. So we can see there are a number of features, as well as a label, which we'll get to now, which is effectively the class column. So just to recap where we are with fraud detection. So within machine learning, there are traditionally 2 main types of modeling approaches. The first being the supervised learning approach, and that is the case where our data has a label or a target variable, which is effectively something that we're trying to learn and to predict, as well as to correct ourselves against. So in this context, this class column contains the label or the target variable, and that merely indicates whether the customer or the transaction was fraudulent, yes or no. That case specifically is the first type of supervised learning, which we call classification. That's where we are predicting a categorical variable. And in this case, it's fraud, yes or no, which means that it's a binary classification problem, meaning there's 2 outcomes, yes or no. We can also have a multi-class classification where we've got more than 2 classes. Then the second supervised learning approach is regression, and that's where we are attempting to predict a continuous value. So for example, it could be price of a house or price of some sort of a product. Then the second main type of modeling approach used is unsupervised learning, and that's where our data has no label at all. So effectively we could cut off this label, remove it from the data frame, just look at the features, and then we could cast this as a unsupervised learning problem if we wanted to. But in this case, we are fortunate enough to obviously have labeled instances of historical fraud, which is useful and meaningful. So in this context, we're definitely going to keep that label. Within unsupervised learning, there are 2 main approaches. The first being clustering. That's when we are trying to find the natural groupings within a data set. Then the second case is dimensionality reduction, and that's where we're looking to reduce higher dimensional data down into a lower dimensional space. So what that effectively means is taking a data set that contains a number of columns, call it 50 columns, and using a variety of techniques. One of them is called principal component analysis, and we're reducing the data down into a lower dimensional space, so from 50 down into 10 columns, for example. And the point of that is to help the model to learn better, to converge better, and overall to help our model performance. Fraud detection, the problem in industry is typically supervised, and it's a binary classification problem, meaning we typically do have access to labeled instances of fraud. Although we don't have a lot of them, we still do have some, but we also get unsupervised cases where we don't have any labels, or we just want to explore the data from an exploratory perspective, and that's where things like clustering can be a very valuable technique. So within this data set, like I mentioned, it represents a supervised learning problem. So throughout the tutorial, we will proceed in a supervised learning manner where we're going to try and predict the class target variable. All right, so back to pandas. What we want to do before we start modeling our data is to partition our data into a data set that can be used for training of a model, and B, a second data set that can be used to evaluate the effectiveness of our model after training. So before we do that, we also want to partition our data into 2 different sets, the one being a data set that contains our target variable only. So we can just slice our data frame and just select the class column, and we're assigning that to a variable y. Then we can take the data frame and we can drop a number of columns, including the target variable. in order to be left with a set of features that we want to use to train the model. So those are just the columns that contain information that can be used to detect fraud, or that we assume as a fraud practitioner that it is informative enough to allow us to detect fraud. So all I'm doing here is dropping these three columns, and this is column Y, so it's going to drop the entire column, and then I'm assigning that to a variable X. Right, so when it comes to model validation, like I mentioned, we want to be able to test our data on a partition of the data after training. Then we also want to train our model on a unique and cleaned up set of data for training purposes. And those need to be separate. So we don't want to encounter a situation where data that was used to train our model is leaked into our test set, which is used to evaluate the effectiveness after training. That's bad practice from a statistical perspective. Rather, we want to keep them separate. First, we start working with our training set, train the model. Our test set acts as a holdout set, which means that we keep it aside. We do whatever pre-processing we need to do in the same way that we pre-processed our training data, but we always keep it aside in our back pocket, and we use it right at the end once we're ready to evaluate the effectiveness of our model. Scikit-learn provides a very nice set of tools to allow us to partition our data effectively. One of them being the train test split module that allows us to pass the X and Y value, and it provides us with a 4-part output, namely the training set and the test set for the X specifically, so for our features, and then the Y train and the Y test, which is the training partition and the testing partition of our target variable, which is Y, right? And as input, the arguments that we supply for this method is the X value and the Y value. We can also select the size of the partition between the training set and the test set. Typically in machine learning, you might hear about a 80-20 split, or a 70-30 split, or a 90-10 split. Obviously, both splits add up to 100%. Depends on the amount of data that you have, but normally an 80-20 or 90-10 split is quite common, meaning that 80% of the data would lie within the training set, because we want to use as many samples as possible for the algorithm to learn from, and then a reasonably sized test set that we can use to evaluate the effectiveness of the model. Right. Then we can also set a random state of 42 to allow for us to reproduce this experiment if we had to rerun and repartition this data over. And then stratification is also very important in a fraud detection context. Because of the imbalanced nature of our data, we're going to have very few positive instances of our target variable. So there's very few cases of fraud. And if we don't specify the stratification, what might happen is all of the fraud might end up in either the training set or within the test set. The stratification, if we stratify by Y, it will split or partition the positive instances according to the distribution across the entire data set. So, if it's 1% of the data is in the original data frame, it'll make sure that that same proportion is preserved when you split into the training and test set, meaning that you will be guaranteed instances of fraud in both cases, which is good because you want to be able to train off the fraudulent instances, and you also want to test the scenario where you've got fraudulent instances in your test set. Right, and then we can take a look at the output of one of these objects. So if we just look at the X train, we'll see it's the training set that we use for our model, which we're going to train in the next lesson. And then if we want to see the number of positive classes within our sample data sets, we can use NumPy, which is a Python library for numerical processing. So we can take the Y train and the Y test. we can use this numpy.where method, and we can explicitly look at cases where the y value is 1. So those are the cases where the fraudulent class is present. And we can print out the length of that effectively. And then we can see, well, within our training set, there are 443 instances of fraud. Within our test set, there are 49, meaning that there's an adequate split. And collectively, if we add those two numbers together, that would be the total number of fraudulent instances in our original data frame.